Hello everybody. I understand that I'm the last one between lunch, so hopefully you still have the time to pay attention to my talk, and I will go to it quite quickly. My name is Hilgerman. I work at Dell as an HPC consultant for EMEA, and today I want to talk about parallel efficiency on HPC. So first of all, I want to start with some definitions, probably common knowledge, but it's often a good thing just to revisit them occasionally. And that is, what is parallel scaling? Well, if I look at the definition of parallel scaling, then you can say that it's generally the reduction of application execution time due to the usage of more cores. So if you look at this table, then you can say that 7x faster on 8 cores is not bad at all, but actually it can be different if you pay more investigation into the numbers. And for that, I would like to revisit Amdahl's law, which has been formulated by Gene Amdahl in 1967 already. And what he said was that the effort that you spend on parallelizing your application becomes ultimately dependent on the serial fraction inside that application. So no matter what you do in parallelizing things, if you have a big serial fraction inside that application that's not parallel, then that will inhibit you from using more cores efficiently. And that, well, speed up factor A is, well, you can put that into a formula that you see down there. If you translate that formula into a graph, and here I have shown a model where I say that my application that I use is 80% parallel. So 80% runs in parallel of my app code, and 20% still runs only in serial. So there's no parallel speed up to be expected. And what you see is that if you go all the way to 32 cores, then ultimately the speed up that you get is only a bit more than a factor of 4 compared to your serial wall clock time. And that is due to the serial fraction that maintains that same 20%. If you would formulate the Amdahl's law differently, and you say, well, I have an infinite number of CPU cores or processors available, then how does that then look like? And then you can see that no matter how many CPUs you are always hitting an upper limit depending on the total parallel fraction of your application. So for a 95% parallel application, you only achieve a 20x speed up. And even for 99 or 99.5%, you are only achieving 100 or 200x speed up. If you then plot that curve differently, where you have the speed up here on the left, and here the number of CPU cores that you have, and you have graphs that are plotted for different parallelization percentages, then you see where the sweet spot is. It is always, for most applications, somewhere between 95 and 99%. Some applications are here between 99 and 99.5, but ultimately you want to be here. Then I have not said about anything about efficiency, but that's actually where it all comes to, because you want to run efficient. You don't want to waste resources on a big supercomputing facility when those resources could also be used for other uses or for other calculations. And what you see here is that I have plotted 3 graphs, one in gray for an application that has an efficiency of 50%, and with that I mean that if I run on 32 cores, I'm still getting a 16x speed up, so I run 50% efficient. And generally what I see also in fields is that this is where you ultimately want to be. You don't want to be lower than that, because then you are wasting resources. So anything above 50% is good. The other ones are for 66%, and the one in yellow is for 75% parallel. And then you see here what kind of percentage you have to achieve in your application, and that's already, if you want to use more than 100 cores, you have to be here for 99% parallel. Just something to keep in mind. So the next topic of my presentation is some best practices, probably common knowledge for some of you, but not for all. And that is that it becomes more and more important to pay attention to your process placement. We have already seen in the other talks that processor affinity and GPUs that are tied to CPU, PCI buses, and especially with the PARATEC languages, that your data locality becomes increasingly important. And back in the SMP days, it always used to be rather straightforward because you had your CPU cores here, they were all on the same bus, and then they were going through a memory controller and they were all accessing the same memory. So you could say that each CPU had the same access time to memory and everybody had the same view of the memory. Then for the x86 world, Intel introduced with the Hilgerman architecture a concept called NUMA. Some other vendors had that already, like SGI for example, but this is about Intel. And what you can see here is that suddenly you have two memories. You have one memory which is local to this CPU and one memory that is local to this CPU, and the CPUs then talk across the QPI bus to each other and to each other's memory. So now you see that the memory access is NUMA, or non-uniform. And with the center-bridge processor, the concept has even evolved further, where the PCI controller is currently on the chip, and then access to PCI devices also becomes non-uniform. So for GPUs, for example, you need to be aware that the cores on this processor core access these GPUs. Oops. And then it becomes even more difficult with the Intel E7, Xeon E7 processors, or the Westmere 4600, where you have 4 sockets and you suddenly have 4 memory domains. For AMD, it's the same. You have 4 more cores, 16 cores in case of the Intel Lagos, and 4 memory domains. So you can imagine that you have to be careful where you run your application on. Luckily, there are tools available in the Linux OS. You have the programming support. You have the SCAD set affinity API, which is defined by the Linux kernel, where you can talk to. You have operating system tools like NUMA control and task set, where you can specify your CPU and memory affinity. And then most MPI libraries either support the kernel mechanism or have their own library bundled with the MPI library that helps you to place the processors correctly. Then I have a case study here. I show you the Gisela plasma physics application that is known to run very well and very efficient on a large number of cores. It uses hybrid MPI and OpenMP parallelism. So generally you say MPI inside between the nodes and OpenMP then inside a node, just to obtain the maximum number of efficiency and performance. And I ran this last year on a single Dell PowerEdge system with the AMD 6276 processors, the fully fledged one, not the one that what Joshua talked about. And this has 64 cores in total. Then what you need to know is that Dell designs its servers for a variety of markets. So HPC is one of them, but obviously there are also other markets where such a system could be used. And if you then look at the processor core enumeration, then you see, hopefully you can read it, is that it is not what you think uniform, but it is very strange, being divided into a deck of 4, where core 0 is here, and core 1 is here, core 2 is then on the other socket, and it roams then around all the cores. So cores 0 to 16 are not on the same CPU, although you would think that they normally are. If you then don't use any placement at all, then what you see is that your MPI ranks and OpenMP threads, so the MPI ranks that have an OpenMP thread associated with them are all in the same color, and you see that they are all scattered across all the CPU cores. And then I get a walk clock time of well, almost 1300 seconds for my Jazella benchmark. If I then use a naive placement, and I say that I assume that MPI rank 0 is on CPU core 0 and that my OpenMP threads are on 0 to 7, then it's somewhat scattered across, but you see already that there's some more organization. And due to the fact that the cores are not roaming across the machine, because OpenMP threads tend to sleep from time to time, and then the Linux kernel preempts them, and then it schedules them again, but probably on a different core, then you see if you don't allow that your walk clock time is already a factor of 5 faster. If you then use a placement script or a placement program, where I'm going to talk on after this, then you can even get better than that. You can get to 6x performance improvement if you take that CPU or that system architecture into account. Then for the PowerEdge 4-socket Intel, it's the same. Again, that's just Strider 4, and I've been told that this has been done to avoid hotspots on various CPUs. So if you do this for cloud type server workloads, then if you spread it evenly, then you save power. So that's applicable to other markets, but not to HPC, where you would like to have your cores fully utilized. Again, the same, and here you also get an improvement if you will place it better, but the improvement is less. In order to accommodate this, I wrote a placement program in C, and it works on Red Hat and on SUSE. It supports all major MPI libraries, from FFmpeg to OpenMPI to HP and Platform MPI and Intel MPI. Some customers use it already on a couple of thousands of cores, and it supports hybrid and OpenMP programs too. It also supports all the major processors, and it knows about these processors. So it knows what the core enumeration is, it knows which cores are sharing level 3 caches, and it also knows, in case of an AMD Interlagos, which cores are in the same module. So it also knows that concept. It only works on Dell systems, just to, well, hopefully to get it used on our systems. And here you have some examples, and you can then see that you just use it on the MPI run line and just before your application. And what you see here, this is on TAC in Texas on a Westmere node, where I have 2 MPI ranks and 6 OpenMP threads per rank. I use OpenMPI. Then you see that the GPU list is again scattered. So all the even cores are on the first socket, and all the odd cores are on the second socket. So it's not only the 4-core Intel or AMD, but also the Westmere dual-core nodes have this. And then you see that the Affinity application plays then nicely on local threads. Here in the case of an OpenMP application, it's the same, where then the memory is shared, so it also places them nicely. And in the case of an AMD Interlagos, then you can see, hopefully that it detects an Interlagos processor and then places the OpenMP threads on separate modules, just to make maximum usage of the bandwidth and the resources on a module. Because in case of AMD, the instruction decoder, for example, is also shared. So here you have maximum execution bandwidth available. Here are some other benchmark results on the Neon refined benchmark for LS-DYNA that you can find on topcrunch.org. I used LS-DYNA 5.1.1 and the latest platform API at the time. I ran again on that same R15 machine, and you can then see that if you use it on 16 or 32 cores, where it has knowledge of the interlagos, that using the placement program gives you a substantial performance improvement compared to that you run it as it is or with the internal process pinning of the platform API library. So architecture knowledge is key. If I have a bit more time, I want to show you some examples of the work I did inside applications. And then it comes to parallel optimization. You see a lot of buzzwords lately, where in the IB space you have FAT3 topologies, I have multi-rail fabrics, my protocol or my data rate is QDR or FDR, I have a non-blocking switch infrastructure, etc. Various API library features where also others have talked about, but firstly start at the root of your parallel performance, and that is load balance or imbalance. If you then see here for a large LS-DYNA calculation at a big customer of Dell, then you see here the core numbers on the x-axis and you see the total wall clock time on the y-axis. And then also partly due to the nature of LS-DYNA, where you have an unstructured grid, so it is hard to do a good decomposition, then you see that some nodes, some cores have more work to do than others. And this inhibits good performance and good scalability, obviously. No matter what you do inside your API collectives or inside your network, this will always hinder you from getting the maximum performance out of your system. You also see it, for example, in the PARATEC computational chemistry application, where you also have a load imbalance in the FFT grid here. The case study that I have goes deeper into this parallel PARATEC workload, and PARATEC is being developed at NERSC, and it does additional electronic structure calculations by using plane waves. And with plane waves, then the wave functions are expressed in Fourier space, but you also have to convert to Cartesian coordinates. So you have to do an FFT, and you also have to transfer your data, because you need to change your grid, and then each processor needs to send its data to a different core, so you need to do an all-to-all type of communication. I ran this at TAC. Dell has a partnership with TAC. This is also where the new big Stampede system is due to be installed. We're currently going on, by the way. And I ran this on the Lone Star cluster, which is number 38 in the top 500. And then if I do a standard G-factor distribution, because I have a sphere, and that sphere is then distributed in rods, and each processor has a rod or some rods, and some at the outside the rods are smaller, and then you have less work to do than inside the sphere where the rods are larger. And then you see that I have a load imbalance here and here. My communication time is around 30%, and my load balance is 21%. And then you see that I have quite substantial wall clock time being spent in communicating or waiting for data to arrive. If I then optimize it, and for this I changed the work distribution scheme in PARATEC, where I sort all the rods first and then I hand those out to the cores, then my load imbalance problem is gone. See, every core has the same number of work to do. And these cores, these systems were, by the way, slower than these cores because it was not a uniform system. So that's then this changed. And then you see that suddenly my communication time has dropped by 10%. So from 30%, I only do now 20% communication, and my load imbalance goes down from 20% to 6%. Much, much better. So my conclusion is actually, out of this talk, that knowledge of the architecture and the system is key to obtain good performance and scalability. And the second message is that there's a lot of talk around MPI libraries and the work being done there, which is very important, by the way, to get good performance on large multi-core systems. But still, don't forget the root, and that is to make sure that you firstly have a good load balance on your workload on your system before you optimize your MPI work. Thank you.